So hi everyone, I'm Luyu Cheng from HKUST. Today I'm excited to introduce a new pattern matching syntax and our translation algorithm. Pattern matching has long been a key feature in functional programming languages, originally introduced decades ago and popularized by ML language family and later by Haskell. Over time, it has been gaining popularity in mixed paradigm languages and even object-oriented languages. Recently, more and more languages have introduced the pattern matching syntax, and some languages don't support it, but their communities are proposing to do so. The remaining languages are either too opinionated or can no longer introduce new syntax. So, what does the syntax for pattern matching usually look like? Let's consider the task of summing up integers from a list of optional integers. We might implement the function sum with the following signature, which takes a list of options of integers and returns an integer. We can make use of pattern matching to implement this function recursively. The body of the function is a pattern matching expression, which follows a structure seen in many programming languages. It starts with what we call the scrutiny, which is the expression that we are matching against different patterns. After this, we have a sequence of cases. Each case consists of a pattern and a corresponding consequence. When evaluating the pattern matching expression, the first step is to evaluate the scrutiny. Then we compare its structure against each pattern, starting from the first and moving to the last. If the scrutiny matches one of the patterns exactly, we evaluate the consequence tied to that pattern and ignore any following cases. However, despite its powerful, traditional pattern matching has some limitations. First, it can only handle one scrutiny at a time. Second, it doesn't allow you to mix patterns with computations, meaning you can't introduce new variables between cases. And finally, nested pattern matching can make code harder to read, especially when dealing with multiple expressions that require nested pattern matching. To address these issues, we introduced the ultimate conditional syntax. In the following discussion, we will refer to this new syntax as the UCS. Okay, so now let's revisit our early program and see how it looks when rewritten using the UCS. The structure remains similar. We still have the same scrutiny, but we replace the match keyword with a more intuitive operator is. The connection between the pattern and the consequence is now indicated by the keyword then. We start a new line. Note that we start a new line after the keyword is, and the cases in pattern matching are indented and come after the is operator. We call this form of syntactical structure split. We can generalize this to normal binary operators. For example, we can split the condition after the equality operator. In this case, within the function, we compare the variable v with space and tab characters. If neither of them work, the else clause is evaluated. This approach allows us to handle multiple conditions efficiently and clearly because they share the same left-hand side. Similarly, we can also start a split before the binary operators. In this example, we are calculating the sign of parameter x using different operators. The else clause still works. This is the first aspect of the UCS. We call this feature conditional splits. That's not the full picture of the UCS. In UCS, the is operator isn't limited to being used against multiple patterns. It can be actually a binary operator and used with just one pattern, acting more like a condition. This flexibility allows the is operator to serve as both pattern matching and a conditional. And moreover, we can introduce more than one pattern matching in a single expression using the AND operator. It serves as a logical conjunction. And what makes life better is that the variables bound in patterns are immediately available in the following logical continuation, no matter the connective is and or then. We call this feature pattern flowing. Next, let's go back to the sum function again. Oh, sorry. Next, let's move to a new example, which I love the most. We can actually combine two aforementioned features. Here's an example. Here we have ADT definition of typical binary search tree. The insert function inserts the given value to the given tree. We first check if T is null or empty. We have seen this before. And the point is that we can attach nested splits to the logical continuation of the first case. We can even split after the left-hand side value and before the operator. This makes this function really concise. Finally, we introduce the last feature of the UCS, which is called interleaved let bindings, which allows computations between cases. Let's consider a program that normalizes a variable TP1, it binds the result to TP1n. If it is, we return and checks if it's of type bottom. If it is, we return an instance of bottom. We then repeat the same process for TP2. Within the UCS, we can access declared let bindings in the following cases. So we can do pattern matching over TP1n and TP2n again. This keeps the code clean and readable. But without the UCS, achieving this would require nested pattern matching, leading to multiple levels of indentation and making the code difficult to follow. With the UCS, we maintain a single level of indentation. Okay, so in summary, we have introduced the three main aspects of the UCS. We have inline pattern matching with the operator is, pattern flowing with logical continuations, and interleaved let bindings. Although the UCS is versatile and flexible, it can be translated back to traditional pattern matching expressions, allowing us to benefit from its expressiveness without losing the opportunity to reuse optimizations and compilation techniques designed for normal pattern matching. So how do we translate the UCS to normal pattern matching? Let me introduce the UCS translation, which has 5 stages. We are going to go through the stages one by one. First, let's look at the source abstract syntax, which is basically a formalized version of the superficial syntax. In the source code, we create a tuple of 2 variables, x and y, and match them against the pattern sum and none. The source syntax on the right look almost identical to the source code except we use braces instead of indentation. Next, let's see how to desugar the source syntax to the core syntax, which is a more compatible, concise, and formalized syntax without that many sugars. So let's look at the scrutiny first. We notice that it is not a variable. So we first create an interleaved let binding from the scrutiny because it's not a variable. Then we go through the patterns one by one. The pattern of the first case is a nested pattern. So we start from the outermost pattern, the outermost constructor pair. We create a flat pattern matching and test it and then we introduce the 2 sub-scrutinies, x1 and x2. Then we handle the first sub-pattern, which is already flat, so we just go ahead. We apply the same process to the second sub-pattern, and finally, we reach the consequence. So now we can generate a term in the end. The treatment of following cases are almost the same, so I'll show you the result. As you can see, the desugar is very simple and straightforward. In our implementation, it can be even on the fly. The outcome is what we call the core abstract syntax. We want to point out that the evaluation of this syntax relies on backtracking. As you can see, each case, because the evaluation semantics goes from the first case to the last case, so there are many repetitive tests. To address this, we introduce a stage called normalization, which normalizes the core abstract syntax to what we call normalized core abstract syntax. As you can see on the right-hand side, the repetitive tests repetitive tests are factorized. So next, we move to the post-processing. Because people can match anything they want at any position in the UCS, so we need some heuristic to reorder matches without affecting the semantics to make the produce the pattern matching. Produce the pattern matching expressions look better. So now let's look at a bad UCS expression first. So why it's bad? Because it doesn't match scrutinies at the same level. As we can see in the first level, we match x1 and x2 at the same time. So on the right-hand side is the outcome of the post-processing stage. Next, we move to the exhaustiveness checking. Let's look at the source program first. The exhaustiveness checking doesn't accept this term. Because in this term, x is matched against some and none, and y is also matched against some and none. There are 4 cases in total, and all of them are presented in the term. So if we remove the second case, the checking phase will report a missing case. And if we remove the first case, the checker can also detect this. But what if we remove the two first cases? The exhaustiveness checking doesn't produce any error. This is because in the matching record, in the exhaustiveness checking information there, x is only matched against none in this term. So there are only 2 possible cases. So actually, our entire translation algorithm is type system agnostic. And in our implementation, missing cases are combined with type errors together. So in summary, our syntax and the evaluation rules are untyped, and we have a straightforward desugaring algorithm. Also, next, I will present the proof of our semantic preservation. And lastly, we have the type system agnostic exhaustiveness checking. So since time is limited, I only show you the intricate part of the proof. The main theorem just shows up if a term evaluates to a value, then the normalized term evaluates to the same normalized value. And what makes things difficult is that our normalization algorithm requires variables to be maintained in the split, even during evaluation. But the beta reduction eagerly replaces all the variables with evaluated values. So in the core lemma, we need a substitution holding the nested normalized terms. Let's move on to the implementation. We have implemented this syntax and the translation algorithm in ML script. We have written a lot of test cases to make sure that they demonstrate our uses and the validation. We also created an online playground at this domain. I think you can have a try. In the future work, we'd like to elaborate the operator OR. Note that we introduced the operator AND in our current syntax. The introduction of operator OR is not straightforward because it might break the non-backtracking algorithm in the non-backtracking trait in our algorithm. Next, we'd like to explore a more tightly integration approach with the type system, especially with the type system of ML script. Next, we'd like to introduce some user-defined patterns and synonyms. For example, here is a syntax we are trying to implementing right now. Lastly, we'd like to introduce some optimizations by heuristic. So here is an example. In our current algorithm, we match the sub-patterns, namely x, y, z, in this example one by one. So from left to right. So it will produce a decision tree like this. There are many duplicate tests and the duplicate consequence. So if we try to match y first instead of x, we can the algorithm can produce a smaller tree, but maintain the same semantic. Okay, so that is the end of my talk. Thanks for listening.
I think we have time for exactly your question, so that's perfect.
Really cool talk. I'm a big fan of this. I guess the question that I had was about like how far-reaching this is. I have all these ideas in my head about like how to rewrite code that I've written before. The two main other like conditionally syntaxes that I'm familiar with are do notation in Haskell and the question mark operator in Rust. Does this like replace either of those at all, or are those still like necessary in conjunction with this?
I think they can both exist. We specially designed the UCS here as an untyped version so that people can introduce it to other languages.
Cool, thanks.
Very nice work. So I have a question about the motivation of you introduce the feature of using let bounding in your pattern matching code. Because our feeling is the old pattern matching code, though like it's not flexible, but it's easy to see like whether the program has pattern matching all the cases. But if you like put enough nested condition or let bounding inside the pattern matching code, it will more like the plain old code, like using let expression and nested if. So can you elaborate why like your syntax may be better to handle in this case?
I think our syntax, one point of the UCS is that we can, is that you can, for example, there's a function in your old code which may use some if then else and some let bindings and some pattern matchings at the same time, and they are interleaved, right? I mean, they are deeply nested, but then you can, and they may also share some like some fallback values. Yeah, like if you have multiple pattern matching and in the wildcard branch, you have the same expression, but with the UCS, and since the all cases are embedded in a single expression, so by the falling through semantics, I mean the evaluation from the first case to the last case, they can, for example, you can save a few lines of code by sharing the default branch.
Thank you.